After completion of the discussion about alkyl halides and their classification, the IUPAC nomenclature of alkyl halides. Today we shall try to understand the nature of CX bond, that is carbon halogen bond in alkyl halides. For example, CCl bond in methyl chloride or chloromethane, CF bond in methyl fluoride or fluoromethane, CX bond in tertiary butyl bromide, secondary butyl bromide, and the nature of CX bond in various alkyl halides. For simplicity, here we have taken to understand the nature of CX bond in alkyl halides only carbon halogen bond in methyl fluoride or carbon halogen bond in methyl chloride or carbon halogen bond in methyl bromide or carbon halogen bond in methyl iodide. Why? I shall let you know after about 2 to 3 minutes. Once we understand the electronegativities of C and X, to understand the nature of CX bond, one should remember that the halogen atom X is more electronegative than carbon atom of the alkyl group. Sir, what is electronegativity? The electronegativity is the power to pull the shared pair of electrons. Halogen is more electronegative, means the shared pair of electrons between carbon and halogen C and X in alkyl halides is pulled, is not shifted. There is no transference of electrons. It is just pulled by the halogen atom. Suppose that I am the shared pair. On this side, there is the carbon atom of the alkyl group. On that side, there is the halogen atom. And because of the fact that halogen is more electronegative than carbon, the shared pair of electron is pulled towards more electronegative atom, namely halogen, as a result of pulling of shared pair of electrons. The X halogen atom gets a very small fractional negative charge represented by minus delta. And as the pulling of the shared pair of electrons towards the halogen atom, automatically carbon gets a small positive charge represented by plus delta. Delta stands for a very small fractional charge. And now, because of the fact that from CX bond, both the carbon atom and the halogen atom, they have a definite charge, positive and negative, maybe fractional charge, plus delta and minus delta. It makes the carbon halogen bond a polar covalent bond, because the atoms carbon and halogen linked by the covalent bond, they have a definite polarity, either positive or negative. Positive plus delta for carbon, negative minus delta for halogen. Okay. Now let us go back. I raised the question why we have selected carbon halogen bond from the methyl group. Where X may be fluorine, this is CH3, where X may be fluorine, maybe chlorine, maybe bromine, or maybe iodine. Why not tertiary butyl bromide? Why not secondary butyl bromide, butyl chloride, like that? The answer of this question you will be able to understand only when you have some pre-information about the inductive effect. You might have studied this effect sometime in the past. I shall just brush up. Whenever two atoms are linked by a covalent bond such that one is electronegative, more electronegative than the other, then there is development of fractional negative and positive charges on the bonded atoms, making them, giving them a definite polarity, fractional charges, so that you get a polar covalent bond. It is represented like this. An arrowhead is put between carbon and halogen, and the arrowhead indicates the direction towards which the shared pair of electrons is being pulled. So that in the next step, there is development of fractional positive and negative charges on the bonded atoms. This particular phenomenon in the formation of in the sigma bond, compounds containing a sigma bond, so that they are a single bond, so that they are joined to one another by two different atoms which have different electronegativities. And because of difference in the electronegativity of the bonded atoms, the shared pair of electrons between the two atoms is pulled towards more electronegative atom, which gets a small fractional negative charge. The other atom gets a fractional positive charge, making it a polar covalent bond, and this effect is referred to as inductive effect. Electron pulling effect is known as minus I effect. Electron withdrawing effect is known as minus I effect. Electron giving effect, electron releasing effect is referred to as plus I effect. Now suppose that instead of hydrogen atoms, I put here 3 methyl groups. The methyl groups are such that they have plus I effect. They have electron releasing effect, so that the shared pair of electrons between carbon of the 3 methyl groups and this carbon, unnecessarily there is an increase in the negative charge of the carbon. This is again negative. So there is some difficulty if other groups than hydrogen, because hydrogen is impartial, it is not having minus I effect, it is not having plus I effect, and we can safely study the nature of CX bond in alkyl halides. And now you get the answer why we select CF bond in methyl fluoride, CCl bond in methyl chloride, CBr bond in methyl bromide, and Ci bond in methyl iodide. The answer is because of presence of the 3 H atoms, there is no harm to this carbon connected to the halogen, and we can study the nature of CX bond in the first stage in alkyl halides in a better way. Namely that because X is more electronegative than C, there is development of fractional positive and negative charges. Carbon gets plus delta charge. Halogen X gets a minus delta charge because of minus I inductive effect. Because of minus I inductive effect, you might have studied it sometime in the past, of the halogen atom. Now going back, let us collect more information about the nature of the CX bond in alkyl halides from the following table. It is very well known that fluorine has a very small atom, smallest atom. Chlorine just bigger than that. Bromine, fluorine, chlorine, bromine, iodine. So if this is fluorine, F, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. This is exaggeration, I know, but it is just to get into the fact that fluorine atom has the smallest size and the iodine atom has the largest size, so that in here the size of halogen atom increases from fluorine to iodine. Fluorine has the smallest size, then chlorine, then bromine, then iodine, and the CX bond length as such, because iodine is a bigger atom, the bond length increases in the order CF, that is CH3F, CH3Cl, CH3Br, and CH3I. Bond lengths of CH3I bond is Ci bond in CH3I is more. Bond length of CF bond in fluoromethane is least. What is the bond length measured in angstrom units for CF bond in fluoromethane? From this table you find that it is 1.42 angstrom units, which is least because the other values are 1.77, 1.99, 2.12. What is the bond length of CCl bond in methyl chloride? It is 1.77. What is the bond length of CBr bond in methyl bromide? It is 1.91. And the Ci bond length in CH3I is 2.12 angstrom units. Referring to their bond strengths or bond energies, we find that CF bond energy is maximum 452 kilojoules per mole. CH3Cl, CCl bond energy is 351. For methyl bromide, CBr bond energy is 293, and for methyl iodide, the bond energy Ci is 234 kilojoules per mole. What is the interpretation? What is the meaning? The meaning is that CF bond is a stronger bond than CCl bond, which in turn is stronger than CBr, which in turn is stronger than Ci bond in CH3I. What is the meaning? The meaning is that shorter is the bond, greater is its energy. Shorter is the bond, greater is its strength. Shorter is the bond, greater is its strength. It is our common experience. Take a long thread, just wind over here and try to break it. Tuck, khalas, broken. However, if you take a small piece of the thread, it's difficult to break it. Why? Because shorter is the bond, greater is the energy. Shorter is the bond, greater is the bond strength. So this is about bond energy, this is about bond length, and now something about dipole moment. I assume that you might have studied dipole moment sometime in the past. Before that, I forgot to tell you one more thing, namely that the carbon halogen bond in alkyl halides is formed by coaxial overlapping of sp3 hybrid orbital of carbon, because in alkyl halides carbon undergoes sp3 hybridization, and the hybrid orbitals lie along the line joining center of the corner of a tetrahedron, and then there is overlapping of dumbbell, that is 2p orbital of halogen atom. Thus, how the CH bond is formed? By along the axis by coaxial overlapping of sp3 hybrid orbital of, I might have written this somewhere. Yes, in the formation of CH bond, there is overlapping of sp3 hybrid orbital of carbon and not of, it should be, and p orbital of the halogen atom, so that CH bond is a sigma bond. You might have studied sometime that there are two types of covalent bonds. One is sigma bond, another is pi bond. Sigma bond because of coaxial overlapping, pi bond because of sidewise or collateral overlapping. Okay, I shall give details of sigma bond, pi bond when I give a lecture on orbital theory, hybridization, explanation of hybridization sometime in future. For the time being, let us assume that the CH bond is formed by overlapping of sp3 hybrid orbital of carbon and p orbital of halogen atom, p orbital of fluorine, p orbital of chlorine, p orbital of bromine, p orbital of iodine. So now, as far as the nature of CH bond is concerned, we are familiar with these things. Number one, it is a covalent bond. Number two, both C and X, they get fractional positive and negative charges. Carbon gets a plus delta charge, fractional positive charge. Halogen atom gets minus delta, a fractional negative charge. This is because of pulling the electrons by halogen atom away from carbon, but not shifting the shared pair of electrons. It is just pulling towards halogen, which gets a small negative charge. Then one more thing which was studied is about the nature of CH bond. The CH bond in alkyl halides is formed by coaxial overlapping of sp3 hybrid orbital of carbon and p orbital of the halogen atom, which may be F, which may be Cl, which may be Br, which may be I. So we have studied about number one, the formation of, about the nature of CH bond, how the bond is formed. Number two, the pulling of electrons by more electronegative atoms so that CH bond becomes a polar covalent bond. Number three, about the bond strength. Number four, about the bond length. And the last column indicates the dipole moment. You might have studied dipole moment sometime in the past. I shall just give you A very simple idea, I shall just let you know in short what is dipole moment. Because we are interested while studying the nature of CX bond in alkyl halides, we have shown interest in their dipole moment studies of the CX bond, of the carbon-halogen bond. What is the dipole moment? Remember that the dipole moment is represented by the letter mu and is a product of E into D. What is the meaning? Just wait, I shall let you know. Any molecule, maybe methyl bromide, maybe methyl iodide, maybe methyl fluoride. We are aware of the fact that an atom consists of electrons, protons and neutrons. Neutrons are neutral. Electrons are negative. Protons are positive. And furthermore, we know that an atom as a whole is electrically neutral because the number of electrons is same as number of protons. Now you can look towards a molecule as if it is a gathering, an assemblage, a get-together of electrons, protons and neutrons, such that the entire negative charge contributed by all the electrons is acting through one single point called the center of action of negative charges. Similarly, the entire positive charge contributed by all the protons in the molecule is as if acting through a single point known as center of action of positive charges, or we may call them as the electrical centers of gravity. Center of action of positive charges, center of action of negative charges, and this D is the distance of separation between these centers of action of positive and negative charges for a given molecule. D is the distance measured in centimeters between these two electrical centers of gravity. E is the magnitude of the charge measured in electrostatic units, and distance is measured in cm, so that dipole moment is measured in the unit ESUcm. This mu is dipole moment. This charge contributed by all the protons is same as contributed by all the electrons. Why? Because now molecule as a whole is electrically neutral. It is of the order of 10 to the power minus 10 or some multiple of that, and this distance is of the order of 10 to the power minus 8 centimeters, so that their product is of the order of 10 to the power minus 10 into 10 to the power minus 8 is equal to 10 to the power minus 18 ESUcm. The unit is ESUcm, and the short name for this ESUcm is dBi. We measure dipole moment in dBi. It is 1.847 dBi, 1.860 dBi, 1.830 dBi, 1.636 dBi. dBi is the unit of measurement of dipole moment. Okay. What is visible from these values of dipole moments for these CX bond in FCl-BRI? We find that the dipole moment should regularly decrease with as we move from F to I. F 1.847, Cl should be less than 1.847. Okay, so this is an exception. Then less than that 1.830 and 1.636. Sir, why there is exception? Why the dipole moment of CCl bond from chloromethane is greater than the dipole moment of CF bond in fluoromethane? The answer is very simple. This is because there is much difference in the bond length of fluorine and chlorine. One is 1.42, 1.77, and in the expression for dipole moment, we take into account the factor of distance, dBi. Because there is an increase in the value of D for CCl bond in methyl chloride than CF bond in methyl fluoride. Because of increase in the value of D, exceptional increase in the value of D, the product ED increases, hence exceptionally dipole moment also increases, and dipole moment of CH3Cl, that is CCl bond, CH3Cl methyl chloride is greater than, is more than the dipole moment of methyl fluoride. So now we have collected much information about the nature of CX bond in alkyl halides. Number one, regarding the charges on C and X, indicating that it is a polar covalent bond. Number two, sizes of fluorine to iodine. Number three, bond length. Number four, bond energy. And based on that bond energy, bond strength. Shorter is the bond, greater is its strength. Shorter is the bond, stronger is the bond. Longer is the bond, is not that strong as the short bond. So we have studied their bond energies, their bond lengths, their dipole moments, and why these values we get. This much information is enough. As far as the 12th standard syllabus of board is concerned, this is more than enough. Nature of CX bond. We stop today. In the next lecture, I shall be explaining the various methods of preparation of alkyl halides. Of course, as usual in the beginning, I shall give you the synopsis, the central idea, the general idea of the methods of preparation, and then we shall study the methods of preparation in detail with all finer points in it. I stop today.